Let's next consider analog input and output modules on PLCs. The idea behind analog input and output is that these are signals that have a range of values they can output, not an on-off signal like a discrete sensor. So if you're talking about the level in tank, temperature being measured, pressure, all these things are continuous variables. How do we get these into the PLC? Well, first of all, we have to have some type of sensor that will transform the physical signal, the pressure or temperature, whatever it may be, into an electrical signal. And we've got a couple of options here for getting this data into the PLC. The sensor can convert the data into, a 0 to 20, or more commonly a 4 to 20 milliamp signal, or 0 to 10 volt signal, or some do 0 to 24 volts or 0 to 5 volts. There's many different options here and different reasons for selecting one over the other. Probably the most common in industrial controls is a 4 to 20 milliamp signal for continuous signals. Now the thing is, though, that the interface that brings in this analog signal that reads the voltage or the current from the sensor has to convert it to a digital signal. And so then after it's done, after the PLC has processed it, has to be converted from an analog signal, from a digital back into an analog signal to be sent out, say to a level indicator or something where maybe we're trying to adjust the level in the tank by adjusting the flow rate into the tank or out, something like that. So the point is that these analog signals, although they are continuous, they have to be discretized and converted into a digital signal that the PLC can deal with, because the PLC is a digital type thing. It's a computer, essentially. Now we say that they have infinite resolution, but in reality noise effects and things on the electrical signal affect they change the effective resolution that even the analog signal can send, but that's out of the scope of this course. What we're primarily interested in is the resolution that the PLC offers because of this required conversion from the analog to the digital world and from the digital back to the analog world. There are two basic types of sensing that is done and even outputting of analog signals, and those are current and voltage sensing and current and voltage output. So analog modules, some of them can accept either current or voltage, but these are two distinct categories of signals. You can't just take a simple voltage output from a sensor and wire it up to a current input on a PLC. That doesn't work. It has to match. Now, sometimes the analog signal itself is converted at the PLC, sometimes it's converted somewhere else. And what I mean by that is when you have a thermocouple, for example, it generates a millivolt signal. So this millivolt signal we get from a thermocouple is not usually something that goes straight into the PLC unless the PLC has a thermocouple input module. Most times what's done is the thermocouple connects to what's called a transmitter, and the transmitter measures the millivolt signal, interprets that as a temperature, and sends it on as either a voltage or a milliamp signal to the PLC's analog input. Now, the heart of this whole process for the inputs is the analog to digital converter. It's a circuit that will look at the voltage or the current level and convert it into a number in the PLC. Now, there are different types of analog input modules. Some are bipolar, unipolar, and then resolution will refer to how sensitive these things are. But a bipolar type of input device is something that can accept positive and negative values. So current flowing in one direction and current flowing in the other, which is not common in the current world, but in the voltage world there are some sources that go to positive voltage and negative voltage, and you've got to be able to sense both. So bipolar is by far not common. What's much more common is unipolar, where the signal can only vary in the positive, in one direction, if you will. And so, something like 0 to 10 volts, 0 to 5 volts, 4 to 20 milliamps, all of this. And unipolar is almost exclusively used in current signals. It's very uncommon to have a current signal that will force current to flow one way and then the other. So the sensor is typically made to only send current in one direction, whereas you're more likely to find, if you find a bipolar input module, it's more likely going to accept a voltage input than a current input. Now, resolution is really important. Resolution just explains, if let's say we're interested in pressure, for example, and we want to measure pressure from 0 to 100 psi, okay? What's the smallest change in pressure before the PLC can sense it? Because the PLC breaks up that whole range into steps. And depending on how many steps are available, in other words, how many bit input the PLC has on that particular module, that will determine what the minimum step size is in pressure before we detect the next higher pressure or the next lower pressure you see. So resolution is something that's really important, not only amplitude resolution as I just described, but also temporal or time resolution is important as well. Now, which one would we want to select? Okay, let's go back to the idea that there's current sensors and then there are voltage signals. And basically these two signals are an option. We can choose either one very commonly. Voltage signals are what most people think of when they're just learning and they want to use it, but honestly a current signal is typically the better option. The reason for that is that the current signal can be run for a long distance and is not as sensitive to noise as a voltage signal. If you think about a voltage signal, let's say that we've got a flow rate going through a pipe and we've got a flow sensor measuring it, and the flow rate's from 0 to 100 gallons per minute. Okay, just making up numbers. And the voltage that the sensor is supposed to put out is from 0 to 10 volts. Well, that's all well and good. The sensor may generate our voltage signal at the sensor, but if we connect copper wires to this, and those copper wires run for a long distance, those wires will have resistance in them. And if they have resistance, the voltage is going to drop as you go down the line. And so the measured voltage at the sensing end, where the PLC is, will be smaller than the voltage output from the sensor, and it'll look like the sensor is telling us a lower flow rate. And that's not good. The nice thing about a current signal is that the sensor is, although a little more complicated, a little more expensive, the sensor will control the amount of current flowing through the loop going to the PLC. And so what it'll do is, if the current's not high enough, it just increases its own voltage. So it'll increase, or in a sense decrease its own resistance, depending on whether it's loop powered or externally powered. But the point is that the signal is a current signal, which doesn't degrade even though the wires have resistance in them. So current signals, 4 to 20 milliamp signals, are preferred over 0 to 10 volt signals. And by the way, you might wonder why you wouldn't use 0 to 20 milliamps and have a larger range and therefore theoretically higher resolution. You could use anything you wanted, right? You could use current on the order of hundreds of amps if you wanted to. Why go to 4? Well, if the sensor is not working, then it would produce a 0 milliamp current, right? There'd be no current. And that can be detected easily, and you can tell that the sensor is bad and something's wrong. You can't trust the measurement you're getting from it. So that's the main reason for the 4 to 20 milliamp standard that's common. Now, some loop sensors, or some current sensors, are loop powered and some are externally powered. So you get the one on the left is a so-called 4-wire sensor. It's not that 4 wires are involved in sensing, it's just that there are 4 wires connected to the sensor. 2 of those are power supply and the other 2 are involved in the information flow loop going back to the controller. The controller is represented on the right hand side as the terminal block that would be on the input card of the PLC. The right hand side, extreme right hand side diagram though, shows just a loop where there's only 2 wires going to the sensor. Turns out there are 3-wire sensors as well, but don't worry about those. 2-wire sensors are usually cheaper than 4-wire sensors. 3-wire sensors are a good trade-off between them. 3-wire sensors can have ground loops, but again, don't worry about 3-wire sensors. Often the wires are twisted, and that helps with noise immunity. That's why it's shown here, crossed over. And then the wires are also often shielded. In other words, there's another conductor that surrounds the 2 wires and is grounded, and that keeps outside electrical interference from inducing current onto or voltage onto the wires, which would then cause a different current flow. Now, on the other end, the output side, the heart of that system is a digital to analog converter, where there's a number in the PLC that needs to be output, say to drive a valve that's controlling flow. And what we have to do is take a number in the PLC and convert that to either a current or voltage. Typically, as I said before, current signals are preferred over voltage signals. And these continuous signals can either be inputs to the PLC, 4 to 20 milliamp, or outputs from the PLC, 4 to 20 milliamps. And of course, in this case, we're talking about an output. where we're using a digital to analog converter. Now on the input side you always use analog to digital. On the output it's always a digital to analog. So that's what's going on inside of the analog I/O module that you connect to the PLC, is analog to digital and digital to analog conversion. Now this allows the PLC to control things that require a continuous signal. For example, this valve here may be something that's a proportional valve. In other words, it's not all the way on, not all the way off, it's anywhere in between that you would like to set it. And that way you can control the flow so that the flow in a pipe, say, is not just fully on or fully off, but is throttled to some value that you want it to be, set at and maintain. So generally the way this works is that you've got something that you sense that's an analog sense, and you output an analog signal in order to change the analog sense. So this is a feedback loop, really, where the PLC detects something, like say we want to control the level in a tank. So we've got a level sensor measuring the level in the tank. It's not like the level's on or off. There's continuous range, but we want the level to be at a certain number. Okay, so that information is fed into the PLC. The PLC then can control a valve that is allowing flow into the tank in order to shut off that valve once the level reaches the point where we want it to be. So if the level's low, you might start with flow at 100%, and as the level comes up, then the level sensor responds, and finally the PLC senses when the tank is at the predetermined set point and then shuts off the valve. Now if you think about this, you realize that there's probably a little bit of delay in response, and all that is very important. In fact, the way that you do this in a PLC is very different from the typical ladder logic. Obviously ladder logic can be used to control this type of a system with comparisons and things, but what you usually use is something called PID control, proportional integral derivative control, and it's just math inside of the PLC essentially, and it makes it a lot easier if the PLC manufacturer includes commands and things that allow you to implement it. It's a big topic that's outside the scope of this course. You just need to be aware that there are continuous signals and how they get into the PLC and out through analog to digital conversion in, digital to analog conversion out. And you need to know that probably the most bulletproof method of communication for these analog signals is 4 to 20 milliamp signals. That's what you'll see very commonly at any chemical manufacturing plant or any of these places that use continuous signals. So the nice thing about this is it allows the PLC to make decisions, if you will, according to your code, and it's still ladder logic code, but you can have the PLC control systems automatically, and you don't have to sit there and eyeball the level in the tank and adjust the valve manually. And of course there's as I said, a whole world of considerations in this, because now we've got dynamic response. You might have realized that as the level gets close, you probably want to slow down the flow, because there's a certain amount of liquid in the pipe that all is going to flow into the tank. And so you actually need to stop the valve a little bit before it hits the set point. And this can be much more complicated than what's shown here with this simple feedback loop. There's all sorts of other types of control, but that's a topic for another class.